friends, welcome to Brave Solution Times. For today's video, we are going to see the proof of Theorem 1.9. So let's get into the video. Theorem 1.9. If A is non-singular square matrix of order n, then adjoint A the whole inverse is equal to adjoint of A inverse is equal to 1 divided by determinant of A dot A. So here they have given that A is a non-singular square matrix, and then they have given a thing to prove. Right, first let's write the given part, which is A is non-singular. A is non-singular. Okay, now if A is non-singular, we have two conditions, which is determinant of A will be not equal to 0, and then therefore A inverse exists. Okay, so these are the two conditions which we can apply if A is non-singular. Okay, now let's prove the theorem. First thing, here you can see there is an A inverse here and adjoint A here, right? So that you can use the formula A inverse is equal to 1 divided by determinant of A into adjoint of A. So here the clue is A inverse, right? But we have another formula for A inverse, which is A into A inverse is equal to A inverse into A is equal to I. So here we have another formula. But why I am not using this instead of this is because in the question they have given a clue that there is A inverse and adjoint A. But in this formula we only have A inverse and we don't have adjoint A. But in this formula we have both A inverse and adjoint A. So that's why I am using this formula and I am not using this formula. Okay, and now look at the question which we have to prove. Here there is adjoint A in the left hand side of this equation. So what we are going to do, we are going to keep this adjoint A to the right hand side, and we are going to bring the rest of the terms to the left hand side. Okay, so that will get adjoint A is equal to determinant of A into A inverse. So this is what we'll get. Let's take this as equation 1. Okay. Now, in the question, as usual, you can see that adjoint A, the whole inverse. Here we have adjoint A, and in the question we have adjoint A, the whole inverse. So for that, what we are going to do, we are going to multiply inverse in both sides. So that multiply inverse in both sides. Okay, so if we multiply, we'll get adjoint of A, the whole inverse, and then here we are going to multiply inverse, so we'll get determinant of A into A inverse, the whole inverse. So this is what we get. And the next step is, just let's try solving this. Now let's take the inverse inside, so that we'll get determinant of A inverse into A inverse, the whole inverse. So we are multiplying inverse inside the bracket. So that we'll get this. Here it will be adjoint A, the whole inverse. Right. Now, here we already know that A, determinant of A inverse can be written as 1 divided by determinant of A. Right. And here by the law of double inverse, if A inverse, the whole inverse, is there, then it will be equal to A. So we are substituting A instead of A inverse, the whole inverse. Okay. So if you see, this is the first part which we have to prove, which is A, adjoint A, the whole inverse is equal to 1 divided by determinant of A into A. Now this is what we have proved. Adjoint A, the whole inverse is equal to 1 divided by determinant of A into A. Now we have to prove adjoint of A inverse is equal to 1 divided by determinant of A into A. So we are going to prove this. For that, we are using our first equation. So by 1, what we are going to do is, we are going to replace A by A inverse. So we have to prove that adjoint of A inverse, right? So in the place of A, we are going to replace A inverse, or replace A by A inverse. Now let's replace it. Adjoint, in the place of A, we are going to replace A inverse. So A inverse is equal to determinant of, here there is another A, in the place of A you are going to replace A inverse, and then here there is another A, here you are going to replace A inverse, and here there is another inverse, right? So let's substitute that here. Okay, and now determinant of A inverse can be written by 1 divided by determinant of A, and then by the law of double inverse, A inverse, the whole inverse can be written as A, right? So adjoint of A inverse is equal to 1 divided by determinant of A into A. So this is the second part which we have to prove. We have proved it, therefore you can write it as hence proved. Now let's go to our second subdivision. Determinant of adjoint A is equal to determinant of A, the power of n minus 1. Okay, so they have given this. In here you can see that there is no A inverse, right? So there is no need for the formula of A inverse. But here there is another thing which is adjoint A and determinant of A. So here by theorem 1.1 we are gonna take a formula which is A into adjoint A equal to adjoint A into A is equal to determinant of A into In. Okay, so this is the formula where we have adjoint A and then determinant of A. And now I'm just taking any one of these terms because these both are just multiplied in a reverse order, right? So I'm just taking any one term, which is I'm taking this first term, A into adjoint A will be equal to determinant of A into In. And now in the question you can see that there is a determinant of adjoint of A, right? So for that you are going to multiply determinant on both sides, so that you will get determinant of A into adjoint A is equal to determinant of A into In. So this is what you get, and this can be written as in the form of determinant, which is A into adjoint A determinant, and then determinant of A into In, right? So you can write this as this, you can represent the determinant in the form of determinant. Now let's split this. So for splitting, determinant we will get determinant of A into determinant of adjoint of A, and which is equal to, so here you have to remember one thing, that determinant of A into In, this term can be written as determinant of A the whole power n. Okay, so you have to write this, and you have to just remember this. If there is a determinant of A, then you have to write it as determinant of A the whole power n. Okay, and in the question again you can see that in the left hand side there is only determinant of adjoint A, right? So what you have to do, you have to take the determinant of A as determinant of adjoint A in the left hand side, and you have to take the rest of the terms to the right hand side. So we are going to do that now. Determinant of adjoint A is equal to determinant of A the whole power n divided by, you have to take this to the right hand side, so that you will get divided by determinant of A, right? So here you can see the base are same. You have a formula, right, which is A power n divided by A power m is equal to A power n minus m, which means if the base are equal, you can subtract the powers, right? So if we do that, we'll have determinant of A n minus, here there is a power 1, right? So let's take that as 1 here. So determinant of adjoint A is equal to determinant of A power n minus 1. So this is what we have to prove. So therefore we have proved it. If I can write it as hence proved. Now let's get into our third subdivision. adjoint into adjoint of A is equal to determinant of A power n minus 2 into A. So this is what we have to prove. And in the question they have given a clue that there is an adjoint of A and then there is a determinant of A. So therefore you can use the formula which is A into adjoint A is equal to adjoint A into A, which is equal to determinant of A into In. In the question they have given that adjoint into adjoint of A, so it's a bit of complicated. So what we are going to do, we are going to take this as B. We are substituting that B is equal to adjoint and A to be B. Okay, so now we are going to write the formula based on this B, so that we will get B into adjoint B, which is equal to adjoint B into B is equal to determinant of B into In. Okay, so now we have written the formula based on this. Now we are going to take any one of the element from these two terms, so that we get, I'm taking this first element, B into adjoint B is equal to determinant of B into In. So I'm taking this element, comparing these two elements, right? Now we know the value of B, right? What's the value of B? The value of B is adjoint A. So let's substitute that. In the place of B, we are going to substitute adjoint A, right? So here there is a B, so you have to substitute adjoint A here, and then adjoint, here there is another B. In the place of B, you have to substitute adjoint A. Okay, now is equal to, here there is another B, so you have to substitute adjoint A and then In. Right. Now, here you can see there is a determinant of adjoint A. So in the previous subdivision, we saw that determinant of adjoint A is equal to determinant of A power n minus 1. Right. So we are going to substitute this in our equation, so that we'll get, instead of determinant of adjoint A, we are going to substitute determinant of A the whole power n minus 1 into In here. And then this term will come here as it is. Okay, and now we have to see our question. They have given that adjoint into adjoint of A in the left hand side, right? So what you have to do, you have to take, you have to cancel this adjoint of A, right? So for that, what we are going to do, we are going to multiply both sides with A. Okay, now we are going to multiply A so that we can cancel this adjoint of A here. So let's multiply here. There will be an A into adjoint A, and then similar, you have to write that here, adjoint into adjoint A, which is equal to, here there will be another A into determinant of A power n minus 1 into In, right? So here you can see that A into adjoint A, right? We already know that A into adjoint A is equal to determinant of A into In, right? So we have to substitute this in our equation, so that we'll get, in the place of A into adjoint A, we're going to substitute determinant of A into In, and then this term will be as it is, adjoint into adjoint A, okay, is equal to A into determinant of A n minus 1 into In. Now we already know that in the left hand side there must be only this adjoint into adjoint A. So we are keeping this adjoint into adjoint A in the left hand side and taking other terms to the right hand side. So that we'll get A into determinant of A n minus 1 into In divided by determinant of A into In. So In and In will get cancelled, and there will be determinant of A n minus 1 divided by determinant of A, right? Now you can see that here another base are equal, right? So that if the base are equal, then you can subtract the powers. So what you will get, A into determinant of A power. Here there is already n minus 1 here, and here there will be also 1. If we subtract it there, it will be another minus 1. So therefore you'll get an answer a into determinant of n minus 2, right? So therefore adjoint into adjoint a is equal to a into determinant of a power n minus 2. So this is what we have to prove, and we have proved, therefore you can write it as hence proved. Okay, now let's get into our fourth subdivision. Fourth subdivision. Adjoint into lambda a is equal to lambda power n minus 1 adjoint of a, where lambda is a non-zero scalar. So here non-zero scalar means lambda is a real number which is not a 0. Okay. Now here the hint is adjoint a. So that's why the reason we are gonna take this formula, which is a into adjoint a is equal to adjoint a into a is equal to determinant of a into in. So we are going to use this formula, and from this formula we are going to take any one term. I'm taking the first term, which is a into adjoint a, and comparing with to this with the last term, which is determinant of a into in. Okay, yeah, so in the question here you can see there is only adjoint a, right? So what we are going to do, we are going to keep adjoint a to the left hand side and taking remaining terms to the right hand side. So that you will get adjoint a is equal to determinant of a in, and this will become divided by a, right? And this in is an identity element which is equal to 1. So that let's take that as 1. So on the next step, adjoint a is equal to here divided by a. When it comes to numerator, you can write it as a inverse, right? So a inverse into determinant of a. So this is our adjoint a, right? But here you can see there is another hint that there is adjoint of lambda a, right? So what we are going to do, we are going to replace a by lambda a so that we can prove this theorem, right? So we are going to replace a by lambda a. Now let's replace. Here there is adjoint and here there is a. So instead of a, we are going to replace lambda a. And then is equal to, here there is another a. So instead of a, we are going to replace lambda a. And there is an inverse here. And then there is a determinant. So instead of a, we are going to replace lambda a. Okay. Now, I have already said that if any number comes out of this determinant, that then that element will have a power of n, right? So first let's multiply this inverse inside, so that you'll get lambda inverse into a inverse, and then here while taking lambda outside the determinant, you will get lambda power n and then a determinant of a. And now here you can see that the base are same. The base are lambda and lambda. If the base are in multiplication and they both have the same base, then you have to add the power. So that you will get there is an n here and you have to add this. So n plus minus 1, it will be n minus 1. And then the remaining terms are a inverse and determinant of a. And now here you can see that a inverse into determinant of a is nothing but our adjoint of a, right? So let's substitute that there. So lambda into n minus 1, in the place of a inverse determinant of a, you are going to substitute adjoint of a. So therefore adjoint of lambda a is equal to lambda n minus 1 into adjoint of a. So this is what we have to prove, which is now a question, and therefore we have proved. Then you can write it as hence proved. Now let's get into our fifth subdivision. Fifth subdivision, determinant of adjoint into adjoint of a is equal to determinant of a power n minus 1 the whole square. I guess you have you remember this, right? In third subdivision we have seen that adjoint into adjoint of a. So we have seen the value of this. Here we have to find the value of determinant of adjoint A. So for that we are using the third subdivision, which is adjoint of adjoint A is equal to determinant of A n minus 2 and A. So we are using our third subdivision here. And here in the fifth subdivision, you have to, there is a determinant here, right? So what we are going to do, we are taking determinants on the both sides. So that you'll get determinant of adjoint A is equal to determinant of n minus 2 A, right? So we'll get this. And now, as I already said, if a determinant is taken outside the determinant, which means if a number or a variable which is taken outside the determinant, then you will have determinant of n minus 2. I'm taking this element outside the determinant, so that we'll get the whole power n. I already said this, right? Now the balance will be a determinant A. Here it will be as it is, determinant of adjoint into adjoint A. Okay. Now let's multiply n inside, so that you will get determinant of A. If we multiply n into n, it will get n square minus 2 into n will get 2n and determinant of A. And now you can see that both the base are equal, so that we can add our powers, right? So determinant of A, now we are going to add our powers, so that you will get n square minus 2n plus 1. So this is nothing but we can write this as determinant of A n minus 1 the whole square. So because if we put the formula of A minus B the whole square here, we will get A square, which is n square minus 2 into AB, which is 2n plus B square 1. So I am writing that as n minus 1 the whole square. So therefore, determinant of adjoint A is equal to determinant of A power n minus 1 the whole square. Okay, so therefore you can write it as hence proved. Okay, so now let's get into our last subdivision, sixth subdivision. Adjoint A the whole transpose is equal to adjoint of A transpose. For here we are going to take the formula A inverse is equal to 1 divided by determinant of A into adjoint of A. So remember this, for this subdivision we are going to take this formula. And now here we have a clue that here there is A transpose and here adjoint A of transpose, right? So what we are going to do, we are going to replace A by A transpose. Okay, so if we replace it first, here there is an A. Instead of A, you are going to write A transpose here, and then there is an inverse, so we are going to put an inverse here. And then here 1 divided by determinant of A. So here there is another A. Instead of A, you are going to replace it as A transpose. And then adjoint of, here there is an A, and in the place of A, you are going to put A transpose. Okay, so here you can see that A adjoint of A transpose, and here also you can see that adjoint of A transpose. So you are going to keep this term in one side and take the balanced term to the other side, so that you will get adjoint of A transpose equal to, we will get A transpose the whole inverse into determinant of A transpose. So this is what we will get. And now we are going to interchange this transpose and inverse. Okay, what we are going to do, we are going to take this inverse inside the bracket and put the transpose outside. Okay, this doesn't change anything, but you can use that. And here there is another transpose, and you can see that both have transpose outside, right? So what we can do, we can take that as a whole transpose. So A inverse dot determinant of A the whole transpose, right? Now here you can see that the formula for A inverse, we have to apply the formula of A inverse, which is 1 divided by determinant of A into adjoint of A, right? Into determinant of A the whole transpose. Now you can cancel this determinant of A and determinant of A, and here there is adjoint of A transpose Therefore, adjoint of A transpose is equal to adjoint A the whole transpose, right? So this is what we have to prove. We have proved it, so that you can write it as hence proved. That's it for this video, guys. Thank you guys. Thank you so much for watching. If you enjoyed this video, please hit the like button and make sure to subscribe. See you in the next video. Bye.